So let's start our first lecture on refraction. So refraction here is the next part in optics. So there are three parts. So we completed light and reflection. So now in this lecture we'll talk about refraction. So there are three sections. First we'll discuss refraction and its phenomena of refraction. Next we'll talk about lenses and how images are formed using lenses. And last we'll talk about optical phenomena. So we'll talk about different optical phenomena that uses the principles of lenses. So let's start with section 1, refraction. So the objectives of the course. So after you complete this particular lecture, you should be able to recognize the situations in which different refractions will occur and identify which direction light will bend when it passes from one medium to another medium, and solve problems using Snell's law of refraction. So let's get into the first topic, refraction. What is refraction? So refraction refers to the one characteristic of light of bending. So bending of light when moving from one medium to another medium. So bending of light when it moves from one medium to another medium is called as refraction. So this phenomenon of refraction, why does it happen? So whenever a light ray travels from one medium into another medium, so the only thing that happens is that it changes its speed. So the light ray will change its direction unless it travels along the normal. So remember that unless it travels along the normal, it always tries to change its direction. So how will it change its direction? So this is an example of how light, when you pass it through water, will generally bend. So even though light is in this direction, so it does not go straight, it actually bends a little. So why is it bending? This brings up the question of why is it that speed of light is not a constant. So remember the concept of wave model of light. So the speed of light in vacuum is generally an important constant, but it's far from the truth that it's actually not a constant, but it's constant in vacuum. It's constant in space. So but if you change it into other mediums, such as for example air, glass or water, the speed of light will generally be different and generally always less than the actual speed of light in the vacuum. So you can never have a medium that gives you a speed of light greater than that of the vacuum. So vacuum is the maximum limit of the speed of light. So this brings up the question, how is it happening? Let's take a simple understanding of why it happens. So let's consider that we have a surface, so water surface, for example, let's say a medium. So on this side, let's say there's water. So let's say on the bottom side we have water, and on the top the medium is air. Now we consider the wave theory or the wave model of understanding refraction. What happens when a wave comes in? So let's take a simple understanding of this. So let's say I'm trying to draw a wave. So there is a light wave that's coming onto the surface. So you have a light wave. So if you remember, light wave is a structure which has a transition, generally has a wave structure which is an electromagnetic wave. Now the idea here is to remember that each wave itself has its own wavelength and it also has its own frequency. So when waves go from one medium to another, so when waves go from one medium to another, for example here when they go from air to water, so when they change their mediums, their lambda will change, but the frequency will stay the same. Why is that the case? Let's take a simple experiment. Let's say you're on the beach, and this is the beach, this is the road. Let's say you're running on the road. So when you're running on the road, you're moving at a constant pace. The pace at which you're moving is calculated by stride length. Stride is how much far you're keeping your leg from one another. So the amount of steps that you take will be the same. For example, let's say you started at, let's say, 10 steps, right, per minute, for example. When you're running on the road, you're running at a constant speed of 10 steps per minute. And let's say, for example, from the road you transitioned into the beach. What would happen? So when you start running into the beach, your steps will stay the same, but the medium, because it has changed, the medium in which you are running has changed. Now what you will try to do is you will decrease the length of the step. So you will decrease the length of the step. This here, so in this analogous example, the number of steps per minute represents the frequency, and the length of the step represents the wavelength. So the same thing applies to light as well. So when light goes into this, what happens is the vibrations will try to, so let's take, for example, you have a wave. So when the wave transitions from one medium to another, so notice that this is the wavelength. Let's say, for example, it goes into another medium. What happens here is that notice that this is the vibrational difference, meaning that it vibrates about a mean medium. So the amount of vibration, even though it stays the same, what happens is it decreases the actual way in which the length of the amplitude of the wave. So you decrease the amplitude as well as you decrease the wavelength, because the light wave starts vibrating smaller, and even though it's vibrating smaller because the particles are much denser, the vibrating density also leads to what we call the shorter wavelength, because it's taking a shorter step here. So this here is the understanding of how waves bend. So let's take a simple example again. Let's take the same beach example, glass slab, and there is a light wave that trying to come across this glass slab. So let's say there is a light wave here. Let me draw it with the other color. This is the light wave. So if it goes straight, it would actually have to go straight this way. It would have to go straight this way. But it does not want to go that long, meaning that the amount of time that it is spending inside this medium is too much. So what light does is it bends itself, travels lesser time in the medium, and then again travels faster out to the other medium. Notice that in both these conditions, the wave direction of the light wave stays the same, but the only thing that reduces here is the shortest time difference here. So it doesn't want to stay too long in the medium, so it always chooses the shortest time and shortest path. So it would rather spend less time in the medium and change its original direction than trying to go longer in the medium and trying to go through the medium directly. This here is the understanding of the wave model. So what happens here? The light wave that comes through now, so when it enters the medium, it does not want to vibrate too much, so that it does not want to lose too much energy. So what it will do is it will reduce its amplitude and it will reduce its wavelength. And once it comes right at this point, again it starts to vibrate at the same length as that of the original wave. So here what is happening inside this medium now, it's reducing the wavelength but maintains its frequency. So it would reduce its wavelength but try to maintain its frequency. So because it tries to maintain its frequency, that's the reason why it ends up taking the path and it bends. So it bends. So this is the idea behind the topic. So if you take the analogy of beach and road, for example, let's consider sand and water here. Let's consider another example where, for example, let's say you have you're in the beach, you're in the water. So let's say and you're right here, right? So this is the person that you have. So you're right here, and you want to go into the water. So to go into the water, let's say you're trying to reach this point. There are two paths to reach this point. From here, you could go directly straight onto that point from point A to point B, or you could rather go straight as much far as possible closer to the point and go into the second point. Meaning that, notice that second path here. What are we trying to do in the second path here? So we are trying to spend less time in water. The reason we are trying to spend less time in water, because it takes the shortest time. It takes the shortest time. Notice that this here is the shortest path, right? Here, for example, let's say this is the total distance. For example, let's say this is 10 meters. But in this 10 meters, you are spending 5 meters in the sand and 5 meters in water. Which means, even though it's the shortest time, it takes longer to reach. But let's take the second condition, where you're traveling longer, but you're spending less time in water. For example, let's say to travel this 5 meters, it took, let's say, 5 seconds. And the other 5 meters, let's say it took 10 seconds, because this is a denser medium in water. But rather than going this way, what we did now is, I would rather travel 10 meters, for example, let's say I would rather travel 8 meters in sand and then only 2 meters in water, right? So let's say, for example, let's say there is 3 meters in water. Even though the total length that it takes here is the higher amount of time that it takes here. Notice that this is 5 seconds and 10 seconds. Notice that for each meter, it's for 1 meter. So you're traveling at 1 meter per second here. Here you're traveling at 0.5 meter per second. The same thing happens here as well. In the second part, it takes 8 seconds in the sand, but it takes 6 seconds in the water. Now the total time that you take when you're traveling through the shortest path is 15 seconds. But here, when you take the shortest time, the amount of time that you're spending here is only 14 seconds. Notice the change in the time. This change in time is what you're trying to maximize as much as possible. So this is the difference here for light. So light would rather choose the shortest path than light would rather choose the shortest time than the shortest path. I hope you understand this. Remember that there is a slight difference between shortest time and shortest path. So let me explain this again so that the concept becomes clear. So there are two ways for light to travel. For example, let's take light itself now. So for example, let's say it starts at a point A. So let's say it starts at the point A and it wants to reach this point B here. Right? It wants to reach this point B here. There are two ways for it to do it. One way is to directly go in the shortest path. So one way is to go in the shortest path. The other way is, I would rather travel longer in air and spend less time in the medium. So notice that this path here is the shortest path. This path here is the shortest time. Why is it the shortest time? Remember again, notice the distance. So this is the amount of distance. So this here is the amount of distance I am spending in air. So remember that we are going from air to water. And this is the amount of distance I am spending in water. The second part is I am traveling longer in air and I am traveling shorter time in water. So because you are faster in air than water where you are slower, so which means that if you take the longer time to travel in air and you are taking shorter time to travel in water, what you are doing here is you are saving time. So for example, let's say it took 5 seconds in air and let's say it took 10 seconds in water, right? So let's not take time right now. Let's take the example of the distance. Let's say the total distance here between this point to this point, let's say is 10 meters. In that, the air here is taking 3 meters, so it's traveling 3 meters in air. You're traveling 3 meters in air and you're taking 3 meters, so for example let's say 7 meters here in water. In the shortest time path, let's say you're taking 5 meters in air and 5 meters in water. So because you're slower in water, even though, so notice the distance is longer, which means that you're going to go much slower. For example, let's say you're able to travel at 1 meter per second in water, so in air, which means that the total time that takes it here is 3 seconds, but here it's going to take 5 seconds in this path. Here you're traveling 7 minutes. Let's say for example you can travel at 0.5 meter per second in water. Now you're going to travel at a total of 14 seconds in water. Here, because there is only 5 meters, it's going to take 10 seconds. Now if you calculate the total time taken is 17 seconds. Now notice that it's still the distance is 10 meters itself, but rather than using the same distance, both of them have the same path or the same distance, but what is the time that you're taking? Now here it is 17 seconds. Notice that here it's taken 5 seconds plus 10 seconds, so the combined time is 15 seconds. So because it takes only 15 seconds and here it's taking 17 seconds, so light would choose the path that gives the shortest time. So this is the nature of light. So this is not something that light does on its own. This is the nature of light. So light always chooses the shortest path. Shortest time. So light always chooses the shortest time. Now you can make the counter argument in reverse when you're doing it in the other side, where which side will it bend? This makes the actual case much more easier to understand why light bends in a sense in one direction. So if you look at light in its refractory state, for example if you take this as a structure, so if you consider a light wave here, so the light wave comes straight through to this point. So when it is going from air into water, it tries to go bend, so it tries to bend towards the normal. So remember this here represents the normal, right? Normal is basically a perpendicular to the surface, so it's basically a line that's perpendicular to the surface. So when you're going from a rarer medium to a denser medium, so the light wave bends towards the normal. Again, remember the condition here. Notice that it tries to choose the shortest path through the medium. Now, so that's the reason why it bends towards the normal. Next, if you take the same thing in reverse, the idea in reverse, remember that here in reverse the path will be different, where you try to take shorter time in the denser path and longer time in the rarer path. So now let's take the other condition. Let's say in this example we are going from water, so you are going from water into air. So again, remember this example, this is going to be a little bit tricky. We are going to use the same analogy again, but we are starting in reverse point here. So let's say I am trying to go from this point here on to this point here. So I am starting here A and I am going to this point B. So the path that I can take, there are two paths. One way is the straight path where I can go directly between these 2 points. The other path would be to try to travel as much possible as much distance as possible, as shorter distance as possible. So the other path would be, for example, let's say I would rather go a shorter distance in the medium and longer distance in the air. Now again, remember that this represents the shortest path, but this represents the shortest time. So again, the same analogy, you're going from water into air. So here in the shortest path, noting that you're traveling longer in water, which means that you're going to go slower and it's going to take longer time. In the second path, in the shortest time path, we are taking shorter time in water and you're traveling longer in the air, which means that it's going to reduce the amount of time that it takes to reach the point. So the same argument happens again when water goes from, so when it goes from water to the air. If you take this as the normal, water, the light wave, when it is going from a denser to a rarer medium, it bends away from the normal. So when it goes from water into air, it bends away from the normal. So when you write it, for example, say this is the, so let's say you're going from water into air. So the light wave, it goes straight, but now it tries to take a longer path in the air, so which means that it bends away from the normal. So here light wave comes in like this and it bends away from the normal, so it goes away like this. So notice that this here represents the normal. Alright, so when you're going from a denser to a rarer medium, so the light bends away from the normal. So this phenomenon is what we call the concept of refraction. So these two things, remember the difference between the shortest time and the shortest path. So the shortest path is where you travel longer in the medium, and try to spend more time, but you try to take the shortest. So our light always tries to choose the shortest time. So rather than bending too much, it tries to bend a little and tries to reduce this distance in the denser medium. So this is the property of refraction. So let's continue the topic of refraction. So let's discuss the law of refraction. So I told you that the light travels at a different velocity in a given medium. Now let's take the same example here. So how do we differentiate the way in which light travels in one medium and another medium? So that variable is called as the index of refraction. So it's a constant, and this index of refraction is denoted by n. So it's the ratio of the speed of light in vacuum to the speed of light in that substance. So n here becomes c divided by v. So where c represents the speed of light in vacuum and v represents the speed of light in a medium. So these are the index of refraction for various substances. For example, if you take diamond, it has one of the highest index of refraction, about 2.419. So it is one of the highest. So some diamonds can have up to 2.54. So the higher the index of refraction, the higher the index of refraction, the lower the velocity of light in that medium. So n here is inversely proportional to the velocity of light in the medium. So that's the reason why in air it's not actually 1, but it's actually 1.000293. Only in vacuum it's 1. So in vacuum n is 1. So whenever you have some kind of an interference, there is always a little change in the index of refraction of the law of light. So that's the reason why diamonds look shiny. The reason mainly is because the light gets trapped inside the diamond and it travels at a slower velocity. That's the reason why they shine, right? So that's whenever you see anything that's shiny, for example even eyes, The reason it shines whenever you put light on it is mainly because of the fact that it slows down the velocity of light. So it slows down the velocity of light. Now, so this is the idea here. The law of refraction basically states that what we discussed in the topic of refraction, when I talked about refraction, when light passes from a medium with smaller index of refraction to a one with a larger index of refraction, so for example from air to glass, the ray bent towards the normal. So when it does the opposite, for example, let's say you have N1 and N2. So you're taking two medium. So N1 is the index of refraction of medium 1. Right? So N2 is the index of refraction of medium 2. Right? So let's consider a wave that's passing through the two medium. So for example, it's going from N1, so medium N1 into N2. So if the light wave comes in, so if the light wave is coming in, so then the way it bends depends on what the values of N1 and N2 are. If N1 is less than N2, then the light wave bends towards the normal. So it bends towards the normal. So it bends towards the normal. Now in the same case, if you consider there is a light wave that's coming here, let's consider another, again the same N1 and N2. If the case where that if N1 is greater than N2, then the light wave that comes in, so the light wave that comes in will bend away from the normal. So will bend away from the normal. This here, so here it bends away from normal. This here is the law of refraction. Right? So depending on the index of refraction of the medium, we can classify the medium and we can determine how the light wave bends or refracts in a given medium. So this here is the law of refraction. So for example, here in the first medium you can consider that N1 is air and N2 is glass. Here in the second medium you can consider that N1 is glass and N2 is air. Right? When you have a light wave that's entering from air into glass, the light wave bends towards the normal. When the light wave is going from glass to air, it bends away from the normal. So that's the difference between these two. So this depends on two angles. There are two angles that we use. One is theta I. So theta I here represents the angle of incidence, which you already remembered, if you remember from last lecture. Theta R represents the angle of refraction. Remember that theta R is not always reflection, but here when we are talking of refraction, it's the angle of refraction. So when the light wave goes from air into glass, theta I is generally greater than theta R. But when the light wave goes from glass to air, theta I is less than theta R. So that's the difference between the two of them. So to explain the relationship between the angles and the index of refraction, we use the Snell's law. So Snell's law basically takes into consideration the index of refraction Ni into sine theta I is equal to Nr into sine theta R. So Ni here represents the incident medium, Nr represents the refracting medium, theta I is the angle of incidence, theta R represents the angle of refraction. So this theta R represents the angle of refraction. So this is the idea of the angle of incidence. This here is the Snell's law. So Snell's law of refraction. So that's the reason why whenever, for example, let's consider that there is a cat that's trying to watch a fish. So best example of this, even if you want to do this at your own home, you can try to do this. So just take a glass of water and put a coin in that water. Now when you look at it from the top, the coin looks like it's as if it's a little higher from the ground. This is due to the formation of the image. So the image is formed at a higher position than that of the original position. The reason is because your light rays generally bend when it comes from the water to your eyesight. But for the coin, for example, if you consider the coin, for the coin you look a little higher. Even though you are a little shallower, the coin will look, for the coin you will look that you are a little higher. This is the concept of apparent image formation or the apparent image position. So now let's use the Snell's law and let's try to solve a problem. So here you have a light ray. So the wavelength 589 nanometers produced by sodium lamp traveling through air strikes through a smooth flat slab of ground glass at an angle of 30 degrees to the normal. Find the angle of refraction. So I am going to write the additional data. So here we are going from air into glass, so specifically crown glass. So crown glass has an angle of refraction, the index of refraction of 1.52, and air you can write it as the incidence, which is 1, right? So this is the additional data that we have now. So they are giving you the angle of incidence. So let's write down all the given data from the problem. So let me copy this problem. So here first they have given us theta I, which is 30 degrees. So they are asking you to find theta R. Ni is air, so the value for air is 1. Nr is glass, specifically crown glass, so the value is 1.52. So these values will be given in the exam, so you don't need to remember any of these values. Now let's use the Snell's law. So Snell's law states that it's Ni sine theta I is equal to Nr sine theta R. So Ni here is air, Ni is 1 times sine 30 degrees is equal to Nr is 1.52 sine theta R. So from this we can get that sine theta R becomes 1.00 into sine 30 degrees divided by 1.52. So let's find this value. So if you have a scientific calculator, that would be great, but if you don't have it, just type desmos.com. So this is a website that you can use to calculate. Now so let's try and calculate the value that we have here. So here we are looking at sine theta R equal to 1 into sine 30 divided by 1.52. So always mention it in degrees. So we have sine 30 degrees, that's 0.5. So whatever is the answer times, we are going to calculate into 1 divided by 1.52. So that gives you a value of 0.3289. This is sine theta R, but we want to have theta R. So theta R, when sine goes the other side, it becomes sine inverse of 0.3289. So here just press on functions and you will notice that this sine inverse is here. So just click on sine inverse of and write down the value. So 0.3289. So that gives you a value of 19.202 degrees. This is theta r. So the angle theta r is 19.202 degrees. So this is how you can use Snell's law to calculate the value that they've asked us. Now, so with that we end the first section on refraction.